Stephenson 2-18, also known as Saint 2-18, a colossal red supergiant star located in the constellation Scutum approximately 19,570 light-years away from Earth, is currently regarded by astronomers as one of the largest known stars in the observable universe, with an estimated radius that stretches over 2,150 times that of the Sun, which means that if it were placed at the center of our solar system, it would engulf Mercury, Venus, Earth, Mars, Jupiter, and even Saturn, making it so incomprehensibly large that its sheer size challenges our understanding of stellar structure and stability. And although its exact mass is difficult to determine due to its vast radius and extreme luminosity, it is believed to be less massive than its size suggests, because red supergiants like Stephenson 2-18 are extremely bloated, cool, and luminous stars in the final stages of their evolution, having expanded dramatically after exhausting the hydrogen fuel in their cores and continuing to burn heavier elements like helium, carbon, oxygen, and eventually iron, at which point the core can no longer sustain fusion reactions, leading to the inevitable gravitational collapse and subsequent supernova explosion, a cataclysmic event that may result in the creation of a neutron star, or, more likely in this case due to its size, a stellar mass black hole. And this transformation from a massive main sequence star to a red supergiant like Stephenson 2-18 is not only an astonishing phase in a star's life, but also a vital process in cosmic evolution, as such massive stars are responsible for synthesizing and dispersing heavy elements like carbon, oxygen, silicon, and iron into the interstellar medium through their powerful stellar winds and eventual supernovae, thereby seeding the galaxy with the raw materials necessary for the formation of new stars, planets, and possibly life. And while Stephenson 2-18's enormous radius of over 2.1 billion kilometers, or about 1.3 billion miles, is difficult to visualize, a common analogy used by astronomers and educators alike is to imagine replacing our Sun with Stephenson 2-18, and then realizing that the star's photosphere would reach far beyond the orbit of Saturn, enveloping the orbits of Mercury, Venus, Earth, Mars, Jupiter, and Saturn entirely, and nearly touching the orbit of Uranus, meaning that if Earth were somehow orbiting this star within its outer envelope, it would be incinerated instantly due to the star's surface temperatures, which, despite being much cooler than the Sun's at roughly 3,200 Kelvin, are still thousands of degrees hotter than any terrestrial conditions. And this relatively low surface temperature, a trait common among red supergiants, is due to the star's massively expanded envelope, which diffuses its energy output over a much larger surface area, resulting in a red hue when viewed through specialized telescopes. And although the star is so massive and luminous, radiating over 400,000 times more energy than the Sun, it is invisible to the naked eye from Earth due to its vast distance and the heavy dust clouds that obscure much of the region of the Milky Way in which it resides, specifically the Scutum Centaurus arm of our galaxy, and it is only through infrared astronomy, radio observations, and detailed spectral analysis that scientists have been able to determine its characteristics, including luminosity, spectral class, radius, and approximate mass, though the latter is notably challenging to calculate for red supergiants because of the lack of clear binary companions and the instability of their outer layers, which fluctuate and shed material frequently through powerful stellar winds and eruptions, creating vast clouds of gas and dust that may one day form new stars or planetary systems themselves. And this stellar shedding is part of the reason why Stephenson 2-18, despite being the biggest known star, might not retain its massive envelope indefinitely, as over time, it will lose much of its outer mass before reaching the final collapse that leads to a core collapse supernova, a process that, while destructive on the stellar scale, is essential for galactic recycling and the enrichment of the interstellar medium. And it's fascinating to consider how such an enormous celestial object, so vast that comparing it to our Sun feels like comparing a grain of sand to a basketball, plays such a pivotal role in shaping the future of our galaxy, especially since stars like Stephenson 2-18 are so rare and short-lived, typically existing for only a few million years compared to smaller, more stable stars like our Sun, which can last for over 10 billion years. And during this relatively short lifespan, Stevenson 2-18 burns through its nuclear fuel at a prodigious rate, undergoing multiple stages of fusion within its core, each producing heavier elements until the iron limit is reached, at which point no further fusion can release energy, and the star collapses under its own gra.